Hello all of you. So, welcome to the second lecture of the course on analysis and modeling in chemical engineering. In the previous lecture, I have introduced you to what is chemical engineering, and basically I looked at two important things that chemical engineers do. One is to ensure that the chemical reactions are done in faster manner, cheaper manner and safer manner. And the second thing is that chemical engineers do what is known as scaling up. That means in the chemical labs, we are producing chemicals in grams, so taking it to tons per day, and scaling down. And I give an example of lab on a chip devices where I am going from grams to milligrams or less than that. And I gave an example of ammonia production to demonstrate what exactly goes in the Hubbard and Bosch process and what is the importance of chemical engineering as a discipline in order to achieve these two objectives, whichever I have listed here. So, in this lecture, I will come to the main point of this course, that is, we are interested in the chemical process modeling. How do we model chemical processes is our objective. So, before we do that, the very first thing we need to know is what exactly do I mean by a chemical process, right? And I want to extend the discussion that I had in the previous lecture, where the chemical processes meant chemical reactions, to a more general definition of chemical processes that may or may not involve chemical reaction. For example, if you are heating water and you are going from cold water to hot water, the water chemistry has not changed. Even if, let us say, it becomes a vapor, the chemistry does not change, it remains H2O. In that respect, even if I start from ice, that is also the same molecule H2O, right? And it still has the same chemical structure, and in fact, more or less same bond lengths of OH, and the fact that there is a lone pair there, so there is a angle, that angle also does not change, right. So, there is no chemical change whatsoever if I am going from ice to cold water to hot water to vapor, but there is a physical change, and the property that is changing here is the temperature of the water as a liquid or as a vapor, right. That is also a chemical process. When I am referring to a physical change in the context of chemical engineering, I would also call that as a chemical process. There is no chemical reaction taking place, but still I am calling it as a chemical process. The second example, let us say I am going from graphite and forming diamond. Now, again, both are forms of carbon. They are called the allotropes of carbon. There is a change in the form of carbon, but as such, the carbon remains carbon, right? So, it's not like a molecule, it's like a form in which the carbon exists in a graphite form or a diamond form or in the form of an elemental carbon. This kind of a transformation again is a physical transformation, but we will still call that as a chemical process, right. So, if there is a change in temperature, change in the form, right, and we can imagine change in other properties of the substance, as long as some change is happening, we call that a process, right. Some noticeable change that we can observe, some observable change, if it is happening, we call that a chemical process, right. Whenever what I mean by observable change, right. So, you can imagine that there is an input to a process and there is an output. Input can be, for example, cold water, output can be hot water, right. But if I have to quantify that, I can say, for example, there is the temperature of the cold water, I will call this T in, and temperature of the hot water, let me call it T out. What do I mean by observable change is that my T out should not be equal to T in, right. Here I am talking about temperature as a variable. Let us say I am talking about graphite to diamond. It can be, for example, the fraction of graphite or fraction of diamond. There must be some property in the system that is changing as a result of the process, and that is something that we can detect and observe. Only then it qualifies to be called a chemical process. It is not a necessity that it has to involve a chemical reaction. If it has a chemical reaction, that is also a chemical process, but if it doesn't and there is change in some property that we care about, if it's a measurable change, we call that a chemical process, right? And then if this is not happening, then clearly this T out is going to be some function of T in, and it may depend on other things. For example, how I am heating, what is my heating rate, let's say Q, right? So that Q now becomes a parameter of the system, right? And it dictates how this system is going to behave or how this process is going to behave. So you can have some parameters as well coming in there, right? And this particular thing, whatever I noted down, I will call it as the response of the process. So a response is the relation between the output and the input. So whenever I say output is a function of input, this becomes my response. And until so far, I am not talking about modeling at all. I am simply talking about a chemical process that is actually happening. And in this case of, let's say, going from cold water to hot water, I am actually measuring the temperature of the inlet and outlet, right? I will soon come to the point of modeling. But in here, I am talking about when I say response, that is the temperature change which I am getting in, I am trying to express the output temperature with the input temperature, or in general, any output variable that I am getting in a process versus a input variable, right? This is also called a black box model, in a sense that, of course, there are many things that this process may entail. But if I am drawing in this particular way, I am focusing more on the input and output only, and not on what exactly is going inside the process. It can be a chemical plant and many things may be happening there, or it can be one unit of a chemical plant. It can be some part of that unit, and I will talk about all of that when we talk about systems and all that. But in here, we are focusing only on the net input and net output and trying to find a relation between the output and the input. Okay. So, what is a model? So, a model is a mathematical representation of this process, right? I just told you that there is an input to output relation in a process, but then there is an actual response, that is how the output depends on the input, and there is something that I can get by constructing a mathematical model that mimics the behavior of a process. Let us say, for example, for heating of water example, if I am saying that Q is equal to mc delta T, I am writing a mathematical model. If I know the heat capacity of water, and if I know the mass of the water, and if I know the heat supplied, I can find the temperature change. That is a mathematical model, right? That mathematical model, of course, is based on assumptions that I am making about the system, how the system is behaving, right? And then we must have a way to solve that particular model. Q is equal to mc delta T is a simpler model. We can just solve on a calculator, but I will talk about more complicated models a lot in this course, right? So, we can construct a mathematical model and then solve it, and I can, in that sense, predict what is going to be the output for a given input. But when I am doing this prediction, that prediction depends on the assumptions that I make in the model. There is no guarantee that whatever output which I will get from this mathematical model will exactly match the output I am getting in the actual experimental process. Let us say, go back to the example of Q is equal to mc delta T. Let us say I assume that the heat capacity is constant in the model, but in reality heat capacity is not constant. Heat capacity depends on temperature, right? So, whatever temperature change we get from the model that I wrote, assuming that there is a constant heat capacity, is not going to match with the temperature change that is coming from the experimental model. Why? Because the heat capacity was assumed to be constant, right? So, in general, we can say that a model gives me again a relation between output and input, but that relation is not the same as the actual relation that is coming from the experiment, right? We hope that it should be the same, we hope that it should be close, but a mathematical model is not exactly equal to reality, right? I can, of course, instead of assuming that heat capacity is constant, I could have assumed some functional form of the heat capacity, let us say A plus BT plus CT square. And now the question will change from the fact that the heat capacity was constant and now it is temperature dependent to like how are we evaluating these constants A, B, C, probably from some data on other system, and how does that translate to the current system, how accurate is that, right? So we can keep doing better and better by making the model more and more complicated. But one thing I want you to keep in mind very strongly is that the model is never equal to reality. Model is always unequal to the reality. What we can measure is how close it is to reality, but not, we can never make it exactly equal to the reality, at least for the models that we will deal with in this particular course, right? And as I was telling you that just like heating rate in the previous problem, in general, we can have some model parameters and we can call it unit variables, right? And now, in the case of like going back to the example of cold water to hot water, I only looked at temperature as the variable, but other things may also change, let's say density, or for example, the pressure in the system, right? So, in general, I can imagine that there is not just one variable, you have a set of variables which can change in the process. By the way, this T denotes the transpose, so I want to make it like a column vector, right? And there can be a series of output variables. This X, now a vector of variables, become the input because I am talking about multiple variables. This Y is now a vector of variables, which is the output, and there is a Y tilde, that is the Y which I estimate from the model which I have built, which is again a vector of the variable. Again, this T is transpose in all these cases. And then there are model parameters. In the earlier case, Q was the model parameter, the heating rate, but you can imagine there can be many other model parameters. Let us say, for example, what is the surrounding like, what is the temperature of the environment, right? What is like, what else is cooking in nearby, and things of that sort, right? So there are certain model parameters which I will include in the model, which are called control variables, and I will talk more about that. But there are certain model parameters which will choose to ignore, maybe because their effect is less. Let us say wind is blowing, and I don't want to account for that in the heating of water in a vessel. So, in that case, the wind becomes a disturbance variable. My results or my deviation from the model and the experimental reality is going to depend on the fact of which disturbance variables I have ignored. I can keep on accounting for all the disturbance variable like wind and let us say that outside temperature, things of that sort, and my model will become more and more complicated, right? And it will never get to a form which I can solve easily, right? So there is a choice which I make to consider a part of the variables that affect the process, and that part or a subset I call as control variables. These variables I am basically controlling in my model, right? The similar control you also have in the experimental process. For example, you are doing in a condition of a constant pressure in the experiment, right? That is an experimental control. You are not controlling the wind speed maybe, but you are controlling the pressure in which the experiment is being conducted. So, in that case, the pressure becomes the control variable and wind becomes a disturbance variable, right? So, you can incorporate control variables and disturbance variable both in the experimental setting and also in the model. The model at least must account for the control variables which I have in the experiment. What are the things which I am controlling? Let's say pressure. That control must be there in my model as well. Regarding disturbance variables, are the variables which I don't have ability to control in the experiment, let's say, or I don't choose to control, and those variables probably I want to miss out in the model as well. If I can include, it's great, but if I cannot, then I can miss out on that. But the control variables must be accounted for, right? And we'll talk more about these by examples that I will take. So, I told you that model is not equal to reality, and I gave couple of examples, but let us begin with a much simpler example, not taken from chemical engineering in the first place, right? So, go back to this old story, how Newton discovered gravity. So, he was sitting there and then an apple fell on his head, and he thought why the apple is falling down and not going up. And based on that, he wrote his famous law of gravity. There is a gravitational pull of the earth that is basically ensuring that the apple is falling down, not going up, and that force is given by mass times the gravity, acceleration due to gravity g, and we can find g as something like gm by r square and things like that. And then going further, he also wrote the equation of motion and things like that. Let us think about this very simple example. Is the force on the apple actually equal to just mg? The answer is no, because there can be, for example, a resistance offered by the air. Let us say I replace the apple with a leaf. It will experience more drag and it will not even fall down directly as the apple is doing, right? But the apple also experiences some amount of drag by the air, right? And if the wind is again blowing, then apple will also experience the force because of the wind, right? And I don't know, once it hits his head, there is also, I would say, and force acted upon by the head, and that is rebounding it backward, which is given by his own third law of motion, right? So even this very simple problem where the object is just an apple and it is falling because of the gravity, it is already so complicated that if I indeed happen to measure the force acting on this apple, it will not be equal to mg. And of course, there are ways we can account for the drag and things like that, but that will clearly make the models more complicated. And no matter how many things we account for, there will be something that is still left out in our modeling approach. Let us say, for example, the fact that it is a winter versus a summer, that will change the density of the air above it, right? So, no matter how many approximations or assumptions we will relax, we are still going to have few things which I am leaving out, and that's the reason why the model is not equal to reality, right? So, now compare that to a chemical plant, and you can imagine in this case there was an apple which was falling, a very simple system, but now we have complex fluids, complex solids, in complex geometries of the vessels and things like that. Many things are happening there, many physical changes, many chemical changes, many chemical reactions, right? Many components. So clearly, there is no way we can make an accurate model for that if we cannot make an accurate model of an apple falling from a tree, right? So therefore, I hope I have been able to convince you that a model is never equal to reality. The question is that how good it is. That means how closely the model approximates reality, right? And as long as we are having an error in the model, which is something that I can tolerate, I would say that the model is good enough. And I will talk more about assumptions and things like that. Okay. So, now the question comes, if model is not equal to reality, then why should we model in the first place? Why are we doing this course on analysis and modeling in chemical engineering, right? The reason being that yes, it is true that all models are wrong in the sense that it is not equal to reality, but some models are still useful. If I want to design a new chemical plant or set up a new chemical plant, let us say for ammonia synthesis, the fact that I know Lechtelier principle and the fact that I know about this particular chemistry, I can actually predict the behavior of a system by some kind of a mathematical model, and I can figure out what I am trying to do, whether it will work out or not. Or for example, what should be the size of the reactor which I am putting in, what should be the temperature and pressure of that, and things of that sort. I can at least predict it using a model rather than designing it and figuring out it didn't work, because experiments are going to cost money. Setting up the plant is going to cost money. So, if a mathematical model, if it helps us at least make an estimation of how this system is going to behave, it is better than having nothing to begin with, because you will spend a lot on setting up the facility and figure out that it did not work as intended, right? So, even if the model is not equal to reality, the fact that the model approximates reality is still able to predict the system behavior, the process behavior, and therefore, we can figure out, for example, things like feasibility, things like good design, things like what kind of parameters I should choose for a particular equipment and things like that. And even if it is not going to be highly accurate, it will at least give us some starting point or some estimates of what the system behavior is going to be like. And in many circumstances, it is not even worthwhile to do the experiment. Let us say I want to make a certain reactor and I want to ensure that that particular reactor sustains very high temperatures. Let us say if a fire is caught in the plant, it will be able to sustain that, right? So, clearly I can do an experiment of that, but the experiment is going to be highly unsafe. So, it is not even worth doing an experiment, and very unsafe experiment. On the other hand, I can do a computational model and I can figure out how the behavior at high temperature of that equipment is going to be like, right? It is true that it will not be exactly equal to the reality, but then even an estimation is good enough, because the conduction of experiment is not only unsafe, but it is also going to basically cost lot of money, right? So, in many cases experiments are not a possibility, or experiments are a possibility, but it is expensive, right? So, in those cases models really help, right? And I will talk about examples of other cases where models do help even for a running plant and things like that. But while doing that, keep in mind that experiments are indeed the ultimate truth, and models are going to the philosophy whichever I told about chemical engineering: fast, cheap, safe. The same also apply to modeling as such. The modeling typically are a faster alternative to experiments, a safer alternative, and also a cheaper alternative, because it does not cost anything other than a computer, right? So, typically whatever advantage I had in chemical engineering as a discipline opposed to chemistry, the similar advantage I do have when I compare a model with an experimental approach. Okay. So, now I hope I have been able to convince you with the other examples that the models are going to involve assumptions, right? And clearly you may think that it is better to have lesser and lesser number of assumptions in the model, right? Take an example of, let us say I want to figure out how much milk a cow will give, and let us say there is a way to figure out using some mathematical model of how much milk I can get from a cow, right? Of course, my ideal is to model a cow as the real cow, but somebody can begin with assuming that, let us assume that the cow is a spherical object. There is a running joke called spherical cow. You can look up it in the Wikipedia and things like that. So, somebody can take it as a spherical cow. Now, you will say that of course, this real cow is very far from the spherical cow and we should not be doing this. But tell me, whether are we interested in representing the cow, or are we interested in figuring out if my model gives an estimate of the milk production? If let us say this model, assuming a cow, with whatever math I am doing to figure out how can I compute the amount of milk, and I am not telling you how to do that. If that model for a spherical cow is giving you a measure of milk production that is close to whatever is found experimentally, the typical production in the actual real cows, Why do we care just for the sake of representation to do this complicated model, where we have a real cow, it looks like real cow, but of course you can imagine that something like this geometry is more complicated. There are more features here, at least the white and black color you see in the figure and things like that. And we need to basically think why are we doing this modeling? Just for representation of the system or to predict something? And if that prediction is working fine, why do we care, right? But we can hope that this model may not give you a correct answer, and then we have to make certain assumptions regarding the cow in order to go from this picture to something like this, right? But these assumptions can be made in a hierarchical manner. Let us say a sphere is not working. Let's imagine that you have an object that has 3 legs. In the next step, let us also add a horn, right? And let's say this model works better than the earlier model, I will go with this model. If this model is not working, I will try this one. Maybe then I will try this one, right? So I can keep on lifting assumptions in the model and go towards a spherical, from a spherical cow to a real cow. When I am doing that, you can imagine that the models will become complicated, but the accuracy is going to improve. And now the question is how much accuracy we do need. If I am fine with the answer I am getting with this model, or let's say this model, there is no reason to make a more complicated model of this particular system, right? So keep in mind that the models that we develop always will have assumptions, and it is fine to have assumptions because we don't want to develop a good representation. We want to develop something that estimates the output of this, in this case the milk production, right? As long as that estimation is good enough, and by good enough I means whatever error I can tolerate, I should go with that particular model. So here comes this idea of optimum slopiness. So what I am trying to indicate is it is fine to be slopy. We know that our cow is not same as the actual real cow, or our model is not same as experimental system, not exactly same, right? It is fine to be slopy, but if I am more slopy, I am going to make more error. If I am less slopy, I am going to make less error. But when going from here to there, my computational time is going to increase. If I make more assumptions, it gives rise to more error. If I make less assumptions, it is give rise to increase in the computational time. And therefore, we need to figure out what is the acceptable error I can tolerate, maybe 5% or 10% or 1%, and I should basically stop it there. There is no gain by making a model that is so complicated that you cannot solve it on a computer, or you are wasting too much effort just to go from an accuracy of 1% to 0.9%, right? So we need to agree on an acceptable error that may of course depend on the context, but as long as we agree on the error, there is no point to keep on making the model more and more accurate and more complicated by adding more and more features or reducing the number of assumptions that I am making. Okay. So there are two standard examples in chemical engineering. Let's say in the CSTR, we assume that there is a perfect mixing in the vessel. Now, if you think about it, and I told you in the very first lecture that mixing is never very perfect. There is poor mixing. If you have a large vessel, you cannot imagine that everywhere inside the vessel the concentration is going to be the same. Nonetheless, this model of a CSTR, continuous stirred tank reactor, does predict for many cases the behavior that is quite close to what is found for experimental reactors. And if it does, then this model is okay. We know from the beginning that perfect mixing is almost impossible to achieve, but nonetheless, if it is working, what is the problem with that? Similarly, for a plug flow reactor, we assume that there is no axial mixing and there is a constant velocity all across the radial direction. So there is no axial mixing and there is a constant velocity in the radial direction or along the cross section. right? The velocity is always along the pipe, but there is no radial variation in the velocity, right? Again, it is impossible to achieve because you have learned that at the wall there is a condition of no slip. So velocity profile cannot look like this. Velocity profile should look like this, because at the wall the velocity must go to 0. We are assuming here plug flow. If you think about it, it happens for Reynolds number of the order of infinity. A plug flow is never completely realized, but if I am making the assumption, if I am making estimates which are able to model a reactor behavior of an experimental reactor, what is the problem with that, right? So we are used to making assumptions in chemical engineering, and no matter what model you have seen, it must be involving many assumptions, right? So I'm going to stop at this particular point. In the next lecture, I will talk about what do you mean by systems and subsystems in chemical engineering. How do you basically decide what do we call as a system and subsystem? What is the basic notion of analysis? And then I will go ahead and talk about things like interconnectivity and the system as a sum of subsystems and things like that. So with that, I want to conclude here, and thank you so much.